Just continuing on with what we have had with one-to-one functions, and all right, and from what we have in the textbook exercises with section 3.1, okay, and just a reminder regarding one-to-one functions. Okay, if functions are inverses. And for the first part, we're looking at seeing whether functions have an inverse relation. Okay, so we have that if functions are inverses, then they will compose together as x. And for what we have in the case of section 3.1, okay, we're looking at seeing whether the functions are inverses of each other. And in the case of problem number 32, okay, we have two functions, h of x and k of x. And we have given, okay, for h of x, we have a linear function with 7x minus 3. And for k of x, okay, we have x plus 3 all over 7. And looking at how these functions will compose together, okay, so we have for, let's say for the first part, okay, so we have h composed with k of x. So we're now looking at h of k of x. Okay, and the way we can set this up and say have h of k of x, okay, and so the output function will be in line with h of x. Okay, so with the input at k of x as opposed to x, we can say we have 7 times k of x minus 3. And filling in for k of x, okay, we have x plus 3 all over 7. And followed by the subtraction of 3. Okay, so for what we have in the process case, you're going to have the 7s are going to cancel out. And so we have x plus 3 followed by the subtraction of 3. Okay, and so that is equal to x. Okay, so that first part checks out, and to see if the reverse order also works. So we have for k composed with h of x. Okay, so we have k of h of x. Okay, and okay, so you got k of x is equal to x plus 3 over 7. And with the input at h of x, so we got h of x plus 3 all over 7. And just filling in. Okay, so for h of x, okay, so you have 7x minus 3. Followed by the addition of 3 all over 7. And what's going to happen, okay, is that you got negative and positive 3 will cancel. And we got the numerator, okay, with 7x remaining. And so we have the ratio 7x over 7. And that's going to go to x. Okay, so we have both compositions to land at x, and so for these functions, yes, they are inverses. Okay, and in the case of the next item, okay, and we have with, let's see, our functions, we have p of x and q of x, and we have in problem 34, okay, we have another linear and rational function, and so we got p of x, and that is given as -3 plus x all over 4. And q of x, okay, we have 4x minus 3. And again, if these are inverses, okay, we'll have those two unanimously compose together throughout as x, regardless of how the order of the functions are placed. Okay, so if we try first part here, say we have p composed with q of x, so we have p of q of x, okay, and so we have the outside function at p. Input, we have q of x, and if I operate in accordance with p of x, okay, but with x in place of q of x, now I'm going to have -3 plus q of x all over 4. And what's going to happen here is that, okay, now for q of x, I have 4x minus 3. Okay. And looking at combining terms together. And what's going to happen here, so we got the variable term at 4x. And now for -3 plus -3. Okay, you're not going to have the negatives in 3 to cancel out. Instead, you're going to have -3 plus -3, so that would be -6. And we have over 4. And if you reduce the ratio, we can break this up. Okay, let's say we have 4x over 4 minus 6/4. Now 4x over 4 goes to x. However, if that was the only reduction that was done, okay, we could go to the next composition. But since we have minus 6/4 or minus 3/2, what happens is that we don't have a clear reduction to x and only x. Okay, and so or x minus 3/2. Okay, that does not equal to x, and you don't even need to go to the other composition. Okay, so for p of x and q of x, whatever relation they have, among the relations, we're not going to have inverses. All right, now in looking at what we have, again, looking at the determination of the inverses of functions, and from the group, okay, now we have for number 47, okay, and throughout we're going to have one-to-one functions. And in 47, okay, so we have f of x is equal to 4 minus x over 9 and exclamation. So we have a kind of a way of expressing a linear function. And now this is a type of one-to-one function that will have the domain and range to consist of all real numbers. There's no restriction on x, And so x can be anything, 0, positive, negative. And the inverse is going to be like in the same situation. Okay, so we're going to have real numbers throughout for the domain and the ranges. Now looking for the inverse. Okay, so just expressing the given one-to-one function, okay, and creating the pathway leading to the interchange of the variables. I'm going to go ahead and write f of x as y. So you have y is equal to 4 minus x over 9. And again, so for the backdrop, okay, so we're creating the interchange between x and y. So upon interchanging x and y, so we're going to have that x is equal to 4 minus y all over 9. And if we look at multiplying the equation by 9, so now upon distributing, we're going to have that 9x is equal to 4 minus y. And for what we have in this case, right, so I'm going to isolate the y term. And so we have subtracting 4 on both sides. So we have 9x minus 4 is equal to negative y. And I can just change the signs at both ends. Okay, so I can either multiply or divide by negative 1. Making y is positive into a negative and vice versa. So we got negative 9x plus 4 is equal to y. And just swapping sides. Okay, so you had that y is equal to negative 9x plus 4. And it's going to follow, okay, that the inverse the inverse of f of x is equal to negative 9x plus 4. Okay, all right. So again, we started out, okay, with our function and putting in terms of y equals 4x minus 9. Again, y is in reference to the original f of x. And after the interchange, okay, the y that we proceed to, that's going to be in reference to the inverse. Okay, so you have y is equal to negative 9x plus 4. And just looking at what we have in this case, so you have, again, for f of x, or y is equal to 4 minus x over 9, and for y is equal to negative 9x plus 4. Again, these functions will have interchanging x and y values. And, okay, so both of these functions are linear. Okay, they are straight lines. Okay, and they will have symmetry with respect to the line y is equal to x. All right, so this is what we're going to have in this particular case for number 47. All right, now for what we have in the case of radical functions, and this time, okay, we have in number 43, okay, we have a cubic root function. And with odd root functions, okay, now we're going to have the domain and the range to consist of all real numbers. Okay, for there's no stuff like the principal square root rule, okay, that creates restrictions in terms of what x can be. Now, in 43, we have the function h of x is equal to the cubic root of x minus 5 Okay, so you have a different letter with h as opposed to f, but it's still going to make reference to y. So you got y is equal to the cubic root of x minus 5 and looking at interchanging x and y. So we have that x is equal to the cubic root of y minus 5. And if I look at cubing both sides to get rid of the radical, so now we'll have the x cubed is equal to y minus 5. Okay, and looking at isolating the variable y, okay, so you have x cubed plus 5 is equal to y. Okay, and switching the order, and we have that y is equal to x cubed plus 5 and we have with the inverse. Okay, so this would be the inverse of f of x is equal to x cubed plus 5. Okay, and again, this will be another case of where we have a one-to-one function that will have all real numbers, okay, for the domain as well as the range, because from end to end, okay, you're going to have the graphs be satisfying the vertical as well as the horizontal line tests. Again, so just looking at the graphs of these, okay, so you got in red, okay, you had the radical function, and this would pass both the vertical and the horizontal line test, and likewise with the inverse, where we have y is equal to x cubed plus 5, and both of these graphs, again, have symmetry with respect to the line y is equal to x, and again, you have your interchanging coordinates, like 2, 13, 13, 2, as well as -1, 4, and 4, -1 among the samples. Okay, all right, so you have one-to-one functions, and again, okay, we have all real numbers, okay, for the domain as well as the range. Okay, and this can be applied for odd root functions, but even root functions, again, would be a different story. And now, and this is going to be a partial lead into, okay, where we do have restrictions, and this one is already imposed. And we have for number 53, okay, so we have f of x is equal to x squared minus 3. And we have that x is less than or equal to 0. Okay, and this is going to be a case of what we have with a one-to-one function. Okay, and okay, I'll give you a case here. Okay, so we got with okay, so if you notice, okay, if I had the graph of all of x squared minus 3, okay, now if you notice, okay, like from end to end throughout, okay, we had to satisfy the vertical line test. Okay, but now for what we have in the case of the horizontal line test, okay, so if you go above, it looks like 0, -3, automatically right away the function is no longer one-to-one. And so to make x squared minus 3 as a one-to-one, and the way this is presented, in case you have x is less than or equal to 0. And guess what? You have just the left half of the parabola. And so it's going to satisfy the vertical line test and the horizontal line test, okay, because with the horizontal line you have intersection at most 1 point, whereas with the right half you had the intersection at 2 points. So this quadratic function, by taking just the left half of the graph, that is one-to-one. And the right half would have been as well if I went with x greater than or equal to 0. And so looking at the inverse of this particular function, all right, so we have f of x is equal to x squared minus 3, okay, whereupon we have that x is less than or equal to 0. Okay, now in the crossover to the inverse, okay, it's going to get a bit analytical. Okay, but we'll still have the same process. Okay, just entering the phase of interchanging the x and the y variables. Okay, so exchanging out, okay, so you have that x is equal to y squared minus 3, and guess what? The restriction imposed for the quadratic function, okay, we're going to have imposed, okay, for y in the inverse. Okay, so in this case, you're going to have that y is less than or equal to 0. And looking at expressing what we have in terms of y. So we get the y term by itself. Okay, so I add 3 to both sides. Okay, so for right now we got x plus 3 is equal to y squared. And I'm just going to swap sides here. So you have y squared is equal to x plus 3. And you don't have to keep writing y is less than or equal to 0 repeatedly, but just to keep in mind that we are going to reference the significance of this inequality. Now for y squared is equal to x plus 3, so I'm going to go from y squared to y. Okay, and so again we have with the square root property of equality, like if you have like x squared or y squared equal to p, you have like y would be equal to plus or minus the square root of p. Okay, but now here we're going from y squared to y. And representing p is not just a single number or letter, but just the binomial x plus 3. Okay, so you had the y is equal to plus or minus, okay, the square root of x plus 3. Okay, and it's going to duplicate what I have here. Okay, now so you got plus or minus the square root of x plus 3, and it can't be both. Okay, so the tiebreaker is going to be, okay, that part of the direction statement version or portion of what we have in the inequality. So we have the less than and the less than or equal to, and if a function is less than 0, then it is going to be negative. So you're looking at the negative portion here. And so for the inverse function, this can be equal to the negative of the square root of x plus 3. Okay, and so just looking at what we have now. Okay, so again, you have y is equal to x squared minus 3 whereupon x is less than or equal to 0. And the inverse of this, okay, we have y is equal to the negative of the square root of x plus 3. And again, the graphs will have symmetry with respect to the line. Y is equal to x. And again, just supplying some order pairs here. I'll do it this way. So you got 0, 1, less than or equal to 6. So you got negative 1. And if I switch the order pairs, okay, so you got, let's say we have negative 3, negative 2, 1, 6, 13, and again you have swapped coordinates throughout. So the one-to-one function, that will be the inverse of y equals x squared minus 3 for values of x less than or equal to 0. We have the negative of the square root of x plus 3. Okay, all right, now going back to our topic, when we cross over to exponential functions, okay, so you have for exponential functions and their inverses, Again, making f of x equal to a to the x as a one-to-one function. Again, we had that the exponential base a was positive with the exception of 1. And again, we had that y, or f of x, is positive. Again, when we had interchanged the variables. Okay, we couldn't do it through the conventional operations to express in terms of y, like by adding, subtracting, multiplying, or dividing. So when we had crossovers to the interchanging, we had x is equal to a to the y. And again, this led to the base a logarithm of x is equal to the base a logarithm of a to the y. And again, bases and logarithms and exponents, okay, they will reduce to the power to which the exponential base is raised. Okay, so you had the base a logarithm of x is equal to y. So you had that y is equal to the base a logarithm of x. And once again, that is going to be our inverse. And again, by definition, okay, a logarithmic function is going to be the inverse of an exponential function. And again, inverse has an interchanging x and y values. Okay, and just a bit of a counterpart here. Like when a was at 10, we had the inverse to be the base 10 logarithm of x. Yes, you have a is at 10, and like in your calculator, you're looking at, if you see just log for your calculator, you're looking at a base 10 logarithm. And again, just for the chart, okay, so you had just comparisons of values. Okay, so you have like x and 10 to the x, like x to the negative 2 is 0.01, x at negative 1, we have 10 to the negative 1 is 0.1. If x is 0, 10 to the 0 is 1. And we have x at 1, you have 10 to the first is 10. X at 2, we have that y is going to be 10 squared, which will be 100. But if I go the other way, okay, you have with x and now y equal to the base 10 logarithm of x. Once again, you have interchanging x and y values. Okay, so we have going from 0.01 negative 2 in contrast to where we have at the end we have 102. Okay, and again, so a logarithm is going to be the inverse of an exponential function. Okay, and now 10 is a special kind of exponential base, and there is yet another. And this is another one of our calculator inputs. And let's say that if you have, like, you're just creating a little bit of a table. So you have, like, for a value x, and then we have 1 plus 1 over x. And say we have 1 plus 1 over x is raised to the x. And just throwing in some numbers here. Okay. So we have, first of all, okay, so you have like chosen values of x, okay, that are positive. Okay, you have like 1, 2, 5, 10, 100, as well as 10,000. Okay, and if I have like x at 1, okay, like you have like 1 plus 1 over 1, 1 over 1 is 1, 1 plus 1 is 2. And with x at 2, now we got 1 plus 1 over 2, or 1 plus 1 half. So it'll be 1.5. And if x is 5, we have 1 plus 1 over 5, or 1 plus 1 fifth. Okay, so that's going to be 1.2. And if we have x at 10, okay, you have like 1 plus 1 tenth. And as a terminating decimal case, that's going to be 1.1. And for x at 100, you have 1 plus 1 over 100. And as a decimal, we have 1.01. And if I have x at 10,000, you have 1 plus 1 over 10,000. And that's going to be 1.0001. Okay, so as x gets larger, the sum value of 1 plus 1 over x is getting smaller. And then clustering together what we have here with the sum as well as the power of x, which will come from these increasing values throughout, we have a 1 plus 1 over x to the x. Okay, we have like 1 plus 1 over x. First case, you have 2 to the x, which is 1. So that is going to go to 2. Say for the next, okay, we had the sum at 1.5. And this will be to the second. 1.5 squared. This will come out to 2.25. Say for the next, if I have like 1.2 to the fifth. And for that number, okay, have among the first digits, you have 2.48832. Then we have 1.1 to the 10th. And you have a number that is just under 2.6. You have like 2.5937. If I have like 1.01 to the 100th, this will be like 2.7048. And you have like 1.0001 to the 10,000th. And you have among the first digits, you have like 2.71814. Okay. And if you notice, you have countercurrent forces happening. The sum keeps getting smaller as x gets larger. Okay, and once you take the sum to the increasing power of x, okay, you notice that x is rapidly expanding, but in terms of the sum to the rapidly expanding power going from one stage to the next, there's really not that much of an increase because we start out with 2 and x is drastically expanded, and we've not gone from 2 to even so much as 3. And there is going to be kind of like the number pi. There's going to be a saturation point that is going to be reached, and like pi, it's going to have an infinite number of decimal places. Like there's not going to be a terminating decimal. And what's going to happen here is that if you were to continue, and say we have as x approaches infinity, what's going to happen here is that for 1 plus 1 over x to the x, so as the exponent gets larger, okay, there's a saturation point that's going to be reached for 1 plus 1 over x to the x, okay, and it's not going to be infinity, because you notice you have like the expanding powers, but there's so little change in the process, and this saturation point is going to be, like pi, it's going to be a letter, and this is going to be the letter E, and that number we have among the first digits, they have 2.718, 281 among the first digits, and for what is referred to as E, E is going to be what is referred to as the natural logarithmic exponential base. Okay, and there's going to be a little bit of code, okay, especially with many scientific calculators. Okay, so just like log is going to refer to a base 10 logarithm. Okay, just like log of x is going to be like log base 10 or base 10 logarithm of x. Okay, now for what you have like alongside log, and this might come as a second function, and it's going to be with ln. And ln is going to refer to a base e logarithm, where e is that 2.718 number. So if you have like ln of x, or the natural logarithm of x, that's going to be the same as base e logarithm of x, again, where you have e to be that 2.718 figure. Okay, now there are applications of the letter E, okay, just like base 10, you have like working with base 10 arithmetic and acid-base chemistry among the other items. And but now for E, you can also have applied in the sciences like chemistry and physics, especially stuff like radioactive decay and all that. But popular approach to applying E, especially where it can also be in the realm of other everyday occurrences, and this will be where we have money matters. If we have like say crossing over into the realm of interest and finance. And for what we have in the case of interest and finance, okay, first of all, and we'll get back to the exponential base e, okay, just kind of using it as a building block. And for what we have in the case of simple interest, okay, now we got okay, variables, multivariable expressions in the mix. You have I is equal to P times R times T. And we have the A is equal to P plus I. Okay. And now one might ask, okay, what do the letters represent? Okay. The letter I, that's going to be the amount of interest. Let me say that for P, that's going to be the principal or the amount financed. And for what we have with R, R is going to be the rate of interest. And this is going to be in terms of a decimal only, without the percent. And T is going to be the amount of time in years. And A, that is going to be the future value. And just let's say on the basis of simple interest. So if you're looking at determining the amount of interest, I and A, if, let's say, we have $1,000, that's what we'll say $10,000. Is borrowed or financed. For 6 years. At a simple interest rate. And we'll say we have a 5%. Okay, so we're looking at determining, okay, what I is going to be as well as A. Okay, so just sort of laying down the bricks. And soon to apply the mortar. Okay, so we have, so you got I is equal to PRT. Okay, so you got $10,000 is financed. Okay, so the P value is going to be $10,000. And R, okay, you have the rate of interest. Okay, you have 5%. But you're going to convert this to a non-percent decimal. Okay, so like, okay, so much percent without, if you apply, convert to a number without the percent, you take that number, divide by 100. So R in this case, that's going to be 0.05. And for the amount of time, okay, we're looking at 6 years. Okay, so looking at what we have now, so we have the principal. Okay, we have it $10,000. And for R, we have 0.05. And we're looking at 6 years. Okay, so if you multiply the numbers all together, it's going to turn out that we have 10,000 times 0.05, and that's going to be 500, and then multiplying by 6, so that's going to be $3,000. And that 5% again is on the basis of simple interest application. So you have future value is going to come from what is financed or borrowed plus the interest. So the interest, again, you have an $3,000 build up, and for the future value, the total amount, principal and interest, okay, so P was at $10,000. And the interest we have at $3,000. And adding together, okay, so the future value A will be at $13,000. All right, so that is in the simple interest. Now, with a lot of credit card companies, they would go and look at applying a different kind of interest, and this is going to be what's referred to as compound interest. And for compound interest, okay, now one version, okay, especially with like the annual compounding, all the way out to say like the monthly compounding, even daily compounding, you're going to have a lot of the variables from the simple interest financing. Okay, so we're going to have A along with P, but this time we'll be looking at exponential applications. So you have like P times the quantity, and we have like plus 1, or I should say 1 plus R over N to the N times T degree. Okay, so you still have the, again, same application for P, the principal, R, rate of interest as a decimal only, T for the time in years, but for N is going to be in reference to the compounding frequency. And there are various descriptive terms. Okay, so if you're looking at annual compounding, okay, so you're looking at one time a year. And if I were to up the frequency, say like for semi-annual compounding, that's like once every 6 months or twice a year. Also have in the case of quarterly compounding, so that's going to be 4 times a year. And for monthly compounding, okay, so we have 12 times a year, once a month. And for daily, oftentimes it will depend upon what financial institution is handling the money. Okay, and some like to stick with the base 10 arithmetic and still kind of have like 360 business days a year, but I'm seeing 365 more and more frequently. So say we have daily, okay, will be 365. And let's say that if you have just an example of compound interest where you're looking at determining the future value. Okay, and we'll say we have determine A given, and we'll say that we have P is at $5,000. And we'll say that we have the time span will be for 6 years. And we'll say that the frequency of the compounding will be done on a semi-annual basis. And we'll say that for the rate of interest, okay, so the quoted percentage rate will have at 3%, and to be able to plug in to the formula, okay, so just writing as a decimal without the percent, okay, so you have 0.03. Okay, so working with the compound interest, where interest is compounded semi-annually. Okay, so you got for P, again we have $5,000. And for 1 plus R over N, okay, so R we have at 0.03. And we have N at 2. And for the N times T power, okay, so you're looking at, you're going to multiply together 2 and 6.
2 plus 6 is 8.
Shut up. Yes, it is. Okay, so you got $5,000. You have times quantity of 1 plus 0.03 over 2. And you have to the 2 times 6 degree. Okay, so looking at the sum, okay, so you got 0.03 over 2. That's going to be a 0.015 added to 1. Okay, so I got $5,000 is for the principal. The sum, 1 plus R over N. Okay, that is going to be at 1.015. Now, N times T, we have 2 times 6 is 12. Now, before I multiply by $5,000, okay, I'm going to take 1.015 to the 12th. And for this number, for 1.015 to the 12th, that's like 12 of 1.015 multiplying out. And for this number, you have like among the first digits, have 1.1956. And multiplying by $5,000. Okay, so in terms of what we have to about the nearest penny, Okay, so you have right at $5,978.09. Okay, and this part, okay, we have with compound interest, we have the frequency to be maxing out on a daily basis. Okay, and now let's say that if one were to ask, can you go beyond daily? Well, theoretically, there is a part to this. If you were to increase the frequency, and say if you have reaching a saturation point, and say we have from our formula, okay, now as n approaches infinity, okay, what's going to happen here is that for this n, as the denominator of r over n, as well as the coefficient in the development of the exponent attained by n times t. Okay. Okay, now the formula is going to be approaching continuous compounding. Or what we have in the case of this item. With our parenthetical statement case, so for 1 plus r over n raised to the n times t power, this is going to become p and 1 plus r over n to the n times t power. As n approaches infinity, this is going to become e to the r times t. And again, where we have e to be that 2.718 figure. Okay, so we have e to apply in the case of what we have with finance. Okay, so now I'll just mention, okay, from example 2, so if you were to determine a, say if $5,000 is compounded continuously, at 3% for 6 years. Okay, so if you're looking at continuous compounding, if it already says continuous compounding, okay, we use this formula. Okay, so you have a is equal to p times e. to the R times T. Again, we had the principal at $5,000. We have times E, and R is still going to be at 0.03. And the time span is for 6 years. And 0.03 times 6, okay, so that's going to be 0.18. Again, the formula in comparison seems simpler, but you got to be careful with the base E. Okay, so we multiply the rate and the time together. So we had the product of 0.18. Now taking E, that 2.718 figure, and raising to the 0.18 power. So you have about 1.197. 217, and just keep the digits and multiplying by $5,000. So you have right at 5,986.09. Okay, and if you notice, okay, with both examples, okay, where we had semi-annual compounding as well as continuous compounding, okay, we had the same principal, rate, quoted percentage rate, and same time span, okay, and you can have the same components, okay, but comparing the numbers, okay, so we had the future value with semi-annual compounding at 5978.09. And with the continuous compounding, you have a little bit more at 5986.09. And the rule of thumb is that with this type of compounding, the more frequently that it is done, the higher the balance will be at the end. Okay, and tell you what, just for the next few moments. Okay, let's see what we get for A. We're to determine A given the following. Okay, we'll say we have first case. We'll say that the principal is equal to $7,000. And we'll say that the quoted percentage rate will be at 10%. And we'll say that n is equal to 12, okay, whereupon we have monthly compounding. And we'll say for the time span, okay, we'll let this be for 5 years. And say that in the other case, so you have $7,000, and the rate is also at 10%. And the time span is for 5 years. And we'll say that interest is compounded continuously. So for the next few moments, let's see what we get for the future value A in these respective cases. Okay, for both of these items, okay, we had the same principal, the same quoted percentage rate, and the same time span. Okay, but we have different frequencies, okay, for the compoundings. Okay, so we have in the first item, okay, so we're looking at monthly compounding. So we're using, okay, the first of the compound interest future value formulas. Okay, so you got P times the quantity of 1 plus R over N raised to the N times T power. Okay, so you got the principal. Okay, so you got $7,000. And for 1 plus R over N, okay, so R we have at 0.1. N we have at 12. Then we have to the N times T power. Okay, so you got $7,000. Okay, now for the sum, we got 0.10 divided by 12. Now, you're going to have a non-terminating decimal. In fact, you're going to have a repeating decimal. So for 0.10 over 12 added to 1, you have this figure like 1.008. And you have repeating 3's throughout. And now for the exponent, you're going to have 60. Okay, and so we have for the numbers. Okay, so if I take 1.0083 and take to the 60th power, okay, you have among your first digits. Okay, so this will be 1.645 3089. Okay, and just let the digits carry on out and multiplying by $7,000. Okay, and to the nearest penny in this case, right? So the future value in this case, after 5 years, you're going to have $7,000 to grow. In fact, it's going to take on an additional $4,500 in interest. So the future value you have right at $11,517.16. And that's going to be for the monthly compounding of interest. And had I had a lower frequency, like if I had annual or semi-annually or quarterly, okay, the balance would be somewhat lower. And in terms of anything more, okay, this would result from taking daily compounding, as well as the other case which we will have for continuous compounding. Okay, so for the continuous compounding, okay, so we have A is equal to P times E to the R times T. And looking at the future value, okay, so you got P again with $7,000. have times e to the r times t. So again, r we have at 0.1. And t we have at 5. So you have $7,000 and e. Okay, so 0.10 times 5, so you're looking at e to the 1/2. Okay, and so for what we have in the case of e to the 1/2, so you have like 1.6487 among the first digits. And multiplying by $7,000. And in this particular case, right, so we have right at 11,541.05. And theoretically, okay, that is going to be the maximum attainable amount, okay, in terms of how the 10% interest can be applied with what we have for the time span as well as for the principal. Okay, so you got with the continuous compounding, okay, you have 11,541.05, and compared to the monthly, you end up with just about $24 higher than the 11,517.16.